Hello, and thank you for joining this session. My name is Yannick Welch, and I'm a principal engineer on the Elasticsearch team. Today, I will give a technical deep dive on searchable snapshots, which allow you to search data in cloud storage at an unprecedented speed and scale. In this talk, we'll look at the key techniques that power searchable snapshots and that make querying large data sets very fast. If you have any questions during the presentation, feel free to use the Q&A feature or directly write in chat. First, I would like to set the stage for what searchable snapshots are and what their use is. As the name suggests, they are based on Elasticsearch's already long time existing snapshot functionality. Snapshots are used to create backups of the data in your cluster to low-cost object stores such as Amazon S3, Google Cloud Storage, or Microsoft Azure Blob Storage, as well as to distributed file systems such as the Hadoop distributed file system. The new searchable snapshot feature now allows you to use these same snapshots in the object stores to directly power your searches. A main use case here is time series data, which can come in many shapes. It can be logs, can be metrics, traces, or it can be security events. If you collect a few terabytes of log data per day, for example, this can quickly amount to a petabyte of data per year. The challenge is to find a way to cost-effectively manage these data volumes while still having the ability to efficiently search on them. Elastic's solution is data tiers, which provide adapted levels of storage and processing power at each of the stages in the data's lifecycle. A hot tier, for example, handles all ingestion of new data in the cluster, and it holds the most recent daily indices that tend to be queried most frequently. As ingestion is a CPU and I/O-intensive activity, the hardware these nodes run on needs good compute power, and they need fast disks. In contrast, a warm tier can handle older indices that are less frequently queried, and can therefore instead use very large spinning disks and less CPU cores. This reduces the overall cost of retaining data over time, yet making it still accessible for queries. With searchable snapshots, we have created two new, cheaper and more powerful data tiers that leverage low-cost object stores. The idea of the code tier is to eliminate the need to keep multiple copies of the data on the disk. Remember that in the hot and warm tiers, half of the disk space is used to store replica shards. These redundant copies ensure fast and consistent query performance, and they provide resilience in case of machine failures, where replica takes over as the new primary. Once the data becomes read-only in its lifecycle, however, redundancy can be offloaded to a snapshot. This means that in the code tier, replica shards are not needed, as in case of a node or disk failure, the data is automatically recovered from a snapshot in the object store, and it's made available for searches already while that recovery is still ongoing. The snapshot repository is perfect for this, since it's much cheaper to store data in S3 than on either local SSDs or on spinning disks. And in most cases, the data is there already for backup purposes. The cold tier therefore only needs half of the local storage space as the warm tier, and it has only slightly worse availability, giving a 50% cost savings over the warm tier. The second data tier that is powered by searchable snapshots is the frozen tier. The idea here is to reduce the amount of compute capacity to a minimum, decoupling the compute from storage by only caching a small part of the data on local disks in the cluster, and then lazily fetching data from the object store on a by-need basis as searches require them. Searches in this frozen tier, of course, in general, slower than in the hot, warm, or cold tiers, as it has to remotely access the data. But this is okay for less frequent searches, for example, an occasional look back as part of a security investigation. In this talk, we'll see how these searches can still be quite fast, even when using remote storage. Before we go into the technical depths of the feature, let's just have a quick look at how it's integrated into the system. It's actually very simple. At the core, it just offers a single low-level API to make snapshots searchable. This API is called the Mount API. When mounting an index from a snapshot using this Mount API, Elasticsearch creates a fresh index in the cluster that is backed by the data in the snapshot, and it allocates shards for this newly created index to the data nodes in the cluster. This allows you to interact with the data in the snapshot as if it was a regular index. It means that you don't need to worry that the data is stored in the snapshot. It allows any and all operations you can do on a regular index, so slicing and dicing the data whichever way you want. When invoking the Mount API, you provide the repository name and snapshot name as parameters where the data is located. The name of the index that is to be mounted into the cluster is specified in the request body, which also has more options which we won't cover here. To distinguish between indices targeting the code or frozen tier, the Mount API has a parameter called storage. If it's set to full copy, each node holding a shard of the index makes a full copy of the data from the snapshot to its local storage. This is what's used for the code tier. And if it's set to shared cache, the shard does not make a full copy of the data, but instead only caches parts of the data in a node local shared cache, which allows for very flexible compute to storage ratios, essentially what we use for the frozen tier. If you use Elastic's ILM functionality, which stands for Indices Lifecycle Management, so if you use that to move the data between data tiers, for example, from warm to cold, you won't have to directly invoke this API, but ILM will internally make use of it. For example, first take a snapshot of the index in the warm tier, and then mount that snapshot in the cold tier. Directly using this lower level API, however, allows for scenarios or use cases not necessarily covered yet by the current ILM integration of data tiers. Now that we have the API covered, let's dive deeper into how the system works. In particular, how searchable snapshots can still very efficiently query the data, even when using the shared cache option in the frozen tier, where only small parts of the data are locally cached. The three key ingredients for why it's fast are a multi-layer caching infrastructure, optimized data access pattern, and optimized data storage formats. In the remainder of the talk, I will expand on each of these, in particular how they contribute to great query performance. Before we go into the details of how the caching layer works, let's start by looking at why such a layer is even needed. So why not have all your data purely on S3 and directly read from there all the time? For that, it's important to understand the caching layers that are already built in today's computer architectures. The exact numbers on the slide don't matter, and they vary by architecture anyway. So this is more to give you an idea of the order of magnitude that we're talking about for these different accesses. It starts with the CPU registers, to a hierarchy of cache levels that reside on the processor. So L1, L2, L3, and it can all be accessed within nanoseconds. Accessing dynamic random access memory, which is also called main memory or DRAM for short, can already take many CPU clock cycles, even on modern systems. And then you have NVMe connected solid-state drives, which, while extremely fast, they are still orders of magnitude slower than main memory. So now we are talking microseconds instead of nanoseconds. Rotational disks are yet another order of magnitude slower, with accesses taking milliseconds. And once you look at blob storage, for example, S3, Google Cloud Storage, or Azure Blob Storage, you will experience latency of tens or hundreds of milliseconds, even when accessing the cloud storage via an instance in the respective cloud provider's compute environment. The motivation for this layered architecture is simple: physics and cost. So each layer allows you to store more data more cost effectively while introducing increased latency. To put these numbers on the slide into more human perspective, the right column in the table has an interesting thought exercise. It normalizes a single CPU clock cycle from 0.3 nanoseconds to 1 second. In this more human consumable form, it's easier to grok the order of magnitude differences in data retrieval delay between the different accesses. The latency of accessing blob storage would amount to years compared to a normalized second latency of a CPU clock cycle. Latency is not the only thing to consider when working with blob store. They have other peculiarities and they differ quite a bit from your local file systems. The first thing to note is that blob stores are typically optimized for large sequential reads and writes, not random access. Fortunately, all of them allow accessing parts of a blob or file via HTTP range headers, where you can specify start and end byte offsets of the range to be fetched. The second thing to note is that blob stores generally provide good throughput, and they scale well with the number of clients. However, an interesting observation here is that they typically throttle bandwidth on the per connection level. On S3, for example, you can at most download 90 megabytes per second per connection. We have observed similar limitations on the other cloud providers. This means that to truly make full use of the available network bandwidth on your compute instances, you have to open multiple connections and you have to parallelize the work, for example, by fetching multiple subranges in parallel. The third thing worth considering, and that we talked about already, is that latency is generally high, so the 2 or 3 digit millisecond range. Note when I say latency, I mean time to receiving the first byte. This high latency can be offset by requesting more bytes in one go. The fourth thing worth considering is that next to your storage costs, you typically have a per request cost associated with retrieving the data from the cloud storage. On S3, this amounts to 0.04 cents per 1,000 GET requests. While this doesn't sound like much, it matters once you start doing many millions of requests. And finally, data transfer costs also need to be considered here. For example, only data transfer from an S3 bucket to any AWS service within the same AWS region is free. While we are going to look in more detail into the data storage formats and access pattern in a few minutes, it should already be clear at this point that we would like to avoid having to repeatedly pay the price of downloading bytes from the blob store, while at the same time also avoid doing too many small requests, but rather request some extra bytes to amortize the cost and offset latency. This means introducing some local cache on the Elasticsearch nodes. Before we go into the details of how that cache works, it's simpler to first look at the cache that already exists on every node and that many of you will be already familiar with, namely the operating system's page cache. The page cache is the main disk cache used by the Linux kernel, and it resides in main memory. In most cases, the kernel refers to the page cache when reading from or writing to disk in order to offset latency of disk seeks. It is completely transparent to applications. When they read from a file on disk, new pages are automatically added to the page cache. If the page is not already in the cache, a new entry is added to the cache and it's filled with the data that's read from disk. If there's enough free memory, the page is kept in the cache for an indefinite period of time and can then be reused by the same or other processes without accessing the disk. Pages are typically 4 kilobytes in size, and they use a least recently used policy for eviction, which replaces the oldest entry, so the entry that was accessed less recently than any other entry. The architecture for the searchable snapshot shared cache that is used by the frozen tier follows similar ideas as the operating system's page cache. The key difference is that it lives on disk instead of main memory. Remember that local disks have much lower latency than blob stores, so caching data there provides faster random access and it avoids repeated downloads of frequently accessed file paths. Similar to how the page cache maps pages of 4 kilobytes in size, the shared cache maps regions of the files in the snapshot repository to the local disk cache in 16 megabyte chunks. The level of granularity is at the level of regions of a file, as we expect some parts of these files to be accessed more frequently than other parts, depending on the query. This means that we don't require the node to have enough disk space to host all the files. Instead, the shared cache manages which parts of a file are available and which ones are not. The on-disk representation is currently just a fixed size, pre-allocated file on which the regions are managed. It is not persistent yet, so does not survive node restarts or crashes. Similar to the page cache, it is populated on cache misses, so whenever a search is accessing a given region in a file. And in contrast to the page cache, which uses a least recently used policy, file regions are evicted in a shared cache based on a least frequently used policy, which works better for large amounts of data, longer latency, and slower throughputs. The cache can fetch multiple regions in parallel, and it will unblock readers as soon as the requested bytes are available, even before the full region has been downloaded. When reading 8 kilobytes from a file, for example, readers are unblocked as soon as those 8 kilobytes from the region are available. The remaining parts of the 16 megabyte region will still continue downloading in the background and will then be readily available once they are requested in follow-up reads. If you're wondering how this cache is actually being used by the system, you can use a stats endpoint that provides information on a per file type basis of what's been downloaded, what's been reused from the cache, evicted, and so on. Finally, it's also worth pointing out that the shared cache is nicely complemented by the operating system's page cache, which avoids actual physical disk access in many cases. Now that we know a bit about the shared cache infrastructure, let's look at the data storage formats and access pattern that make this cache so useful. For this, you have to know that Elasticsearch is using Apache Lucene as underlying storage and query engine. It is actually Lucene files that are stored on disk and in the blob store. We will have to look at how Lucene lays out the data on disk and how that fits our caching strategy. We'll only do this at a super high level in this talk, as Lucene comes with a very powerful set of optimizations to compress the data well and make it fast to access. Lucene uses different on-disk data structures for different access patterns. For example, the most well-known Lucene data structure is the inverted index, which is typically used for searches on text or keyword fields. There are also point structures, which are used for searches on numeric fields. Then there are doc value structures, which are typically used for sorting or aggregating on data. And finally, there are stored field data structures, which are primarily used by Elasticsearch to store the full original source of the document, which is then later retrieved to populate the hit section of the search results. Worth noting is that the inverted index, as well as doc values and points, they organize their data structures separately for each field, even if all the data structures for these different fields are ultimately stored within the same file. This means that if you're only searching or aggregating on a given field, only the region of the file that stores the relevant data structure for the given field will be accessed. To make this a bit more concrete, let's look at an example on the right side of the slide. Let's assume that we have a simple search that matches all cities that are in the African continent, and we combine it with a terms aggregation that gives us all unique country names. This search can use the inverted index data structures of the continent field to quickly run the query part. As the inverted index structures are consecutively stored on a per field basis, it's sufficient to access the file region that has the inverted index for the continent field. In fact, it's not even necessary to access the full file region that has the inverted index. A subset of that file region is sufficient. This means that we only need to download a small subset of the overall index structures and for relatively contiguous regions in the file. For the aggregation part of the search, can use doc values data structure of the country.keyword field to quickly compute the unique countries. Doc values provide, again, a column-oriented view of the data, which means that the aggregation on the country field allows us to only download the columnar data for that field. The columnar nature of doc values also allows for great compression, while at the same time providing fast access. For example, doc values do not store the raw bytes for each document in case of keyword or text field. Instead, they write a separate terms dictionary containing all unique values in sorted order, and then write the indexes of these values in the column store. If the search is also to return some hits, for example, the top 10 matching cities in Africa, it will use stored fields to return the ID and original source of the top matching documents. As stored fields use row-based storage, this will see a lot more random access all over the data structure, so it will benefit much less from caching. Important to note, though, is that stored fields typically see much less access, for example, only retrieving _source for the top 10 matching documents, which might possibly result then in 10 HTTP requests to the blob store. In summary, the advantage of having everything indexed by default in Elasticsearch makes searchable snapshots so powerful, as it avoids doing a full scan of the data, and instead it leverages the index structures to quickly return results over very large data sets by only downloading small contiguous portions of it. If you're wondering how much space is being occupied by each field, and in particular each data structure for each field, we now provide introspection to that with a recently introduced disk usage API, which will tell you how much disk space is taken up by each data structure for each field. Let's look at a concrete example using a production data set to exactly see what this means. So on the upper right, we have a Kibana dashboard using various aggregations, and on the bottom left, we have a chart showing how computing that dashboard translates into bytes downloaded. As dashboards are heavily aggregating, most of the data downloaded is doc values. The main point to take away from this slide is that only a fraction of the overall data in the repository, so what's in red, needs to be downloaded in order to compute the given dashboard. I will provide more performance numbers on this in a minute. First, I would like to point out that for performance-critical workloads, it might be important to have the full data cached. In that case, the cold tier, so the amount option full copy, is best suited. It creates a full local copy of the shard's data from the repository, and it persists the local copy so that it's available after crashes or restarts, making the data locally available again in no time. It uses a different on-disk representation as it does not need to share cache space with other shards. Instead, it uses sparse files to incrementally use disk space as the data is being downloaded. It also allows searchers to proceed before everything's been downloaded by tracking regions of files that are available to be searched and eagerly retrieving missing requested portions of the files. Now that we know more about the storage options and caching layers, let's look at some benchmarks using real-world data sets. The dataset used here is an event-based dataset of web server logs that Elastic is using for benchmarking various features. For simplicity, we benchmark only a single node cluster, but each tier also supports multi-node clusters. The single node cluster is an N2D instance on Google Cloud with 8 virtual CPUs, 64 GB RAM, and local SSDs. It is a suitable candidate instance for Frozen as it has fast local disks for the on-disk shared cache, and it has a fast network connection to Google Cloud Storage, where the snapshot data is stored. We looked at 2 use cases. The first one was just a simple term query that finds occurrences in the data set where a given IP address has access to web server. We mounted 12,500 shards of 80 GB each on our single node cluster, which mounts to exactly 1 petabyte of data that was mounted. Running the simple term query on that full 1 petabyte dataset took less than 10 minutes, showing how well the implementation scales to larger datasets. The second use case is a Kibana dashboard, which we saw on one of the previous slides, that contains 5 visualizations and is designed to be used for analysis of requests with a 404 response code. For example, to find links that are no longer leading anywhere. We ran this on a 4 terabyte dataset. Performance on the cold tier, which has a full local copy of the data, it's comparable to hot or warm tiers. The frozen tier returns the dashboard within 5 minutes, compared to the 20 seconds it takes for the dashboard to be computed in the other tiers with local data access. Computing the dashboard only required downloading a fraction of the data in the repository thanks to the index structure, so approximately 3% in this case. When Elasticsearch's result caches are disabled, the performance of repeat searches mainly depend on the page cache, and they are comparable in performance with the other tiers when the portions of the data needed for the query fully fits into the shared cache. Dimensioning the shared cache on the frozen tier matters in order to achieve good performance for repeat searches. Here, the right value very much depends on the kind of queries that are run, in particular, how much data needs to be accessed to yield the query results. Having large amounts of data mounted, therefore, does not necessarily always require larger on-disk cache. Applying a time range filter, for example, in the context of time-based indices, it reduces the number of shards that need to be queried. As there's often some kind of underlying spatial or temporal locality in data access pattern, the frozen tier will allow efficient querying on very large data sets. Based on our current observations, we recommend sizing the on-disk cache so that it's between 1% and 10% of mounted data size. A ratio of 5% is perhaps a good starting point for experimentation. We have also benchmarked a case where only a slightly different dashboard is computed, for example, filtering by different country code. In this case, the frozen tier can benefit from having already downloaded many portions of the data that are relevant to satisfy this slightly different query, and it returns results nearly as fast as the other tiers. In this last part of the talk, I would like to cover some best practices for using searchable snapshots. The first thing to note is that forced merge data provides enormous speedups when using searchable snapshots. Shards that are not forced merged have many segments, for example, 50 segments or more in a hot index, which makes searching in the frozen tier much less efficient. Data is less collocated as it's split over many files, and it requires more random access, which is slow on object stores. We have observed tenfold speedups of forced merge versus non-forced merge datasets here. And it's worth mentioning that this is automatically taken care of when using indices lifecycle management. The second best practice is to only mount an index from a snapshot whose lifecycle is under your control. Otherwise, the backing snapshot might be unexpectedly deleted. The solution we have for this is the newly introduced Clone Snapshot API. With this, you can create a clone, which is essentially a shallow copy of the snapshot whose lifecycle is now completely under your control, and then you mount that clone instead. A third very important consideration is the reliability of snapshots. The sole copy of the data in a searchable snapshot index is the underlying snapshot, which is stored in a repository. And if the repository fails or corrupts the contents of the snapshots, then the data is lost. Although Elasticsearch may have made copies of the data onto local storage, these copies may be incomplete and they cannot be used to recover any data after repository failure. Fortunately, the blob storage offered by all major cloud providers typically give very good protection against data loss and corruption. If you manage your own repository storage, however, for example, using MinIO or HDFS, then you're responsible for its reliability and you must plan accordingly. We also have a number of recommendations for setting up clusters that use searchable snapshots. First recommendation is to avoid mixing workloads by using dedicated machines for the cold or frozen tiers. The frozen tier, with the shared cache in particular, it sees a different kind of resource usage than your typical hot or warm tier. So in order to keep performance on your ingest heavy or more search heavy hot tier unaffected, it's best not to have different tiers co-located on the same machine. The second recommendation is about what instance types to use for frozen tier nodes and how to configure the shared cache. We recommend instance types that provide fast network access to the cloud storage, as well as have fast disk, for example, local SSDs. So these are suited best for the shared cache. While rotational disks seem like an interesting candidate as cache for blob storage, we found them to not deliver that great performance, especially as we do many parallel writes due to highly concurrent downloads, and having an excessively large local cache isn't really helpful. Note that you should also actually make use of your fast local disk for the shared cache. By default, with 90% of the available disk space, or leave a headroom of 100 GB for other stuff, whichever is largest. The last but very important observation is that both vertical as well as horizontal scaling is well supported by the frozen tier, as the computations can typically be easily parallelized. The unit of distribution is still a shard, so the same model as for regular Elasticsearch indices. So just using more performant machine types, in particular with higher network bandwidth or more CPU, or adding more nodes to the cluster is a simple way to increase your query performance. For example, if you want to run the 1 petabyte query in 1 minute instead of 10, you just use 10 nodes instead of 1, or use more beefy machines. And this concludes my talk. So if there's one thing you should take away from this talk, is that searchable snapshots, they provide extremely flexible compute to storage ratios while being orders of magnitude faster than scanning over a full data set. Thank you.